So yesterday we talked about finding abs. Let the screencast listen to the noise. That way the people who are gone realize why there's going to be a seating chart. Yeah. I'm not going to compete with you. Okay, so yesterday we talked about absolute minimums, maximums for a certain domain. So the key is you take your function, you take the derivative, okay? Wherever it's equal to 0 undefined, that's where you have a critical point. And then what you have to do is take your endpoints, any critical points, plug them into the original function, and see which y value is the highest, that's your max, see which value is the lowest, that's your absolute minimum. I'm going to redo the last problem that we ended with yesterday. Felt like we were a little rushed, and I know not everyone was paying attention, so I'm just going to do it again. So that was absolute, but what about local extrema? What about if I don't want to just know what's the highest absolute value and lowest absolute value? How would we do that? It's very, very similar. First, you explicitly define the domain of your function. Sometimes we restrict our domain, like here, from like -1 to 1. But other times, in the example below, we're talking about a whole polynomial function. All right, find the extremes of the function where they occur. It wasn't restricted for us, so we want to explicitly say the domain is going to be from -infinity to infinity. So you probably already have this written down. If not, we're going to do it again. So we're at the bottom of page 5. Okay, so step 1 is find the domain. Now we want to find the critical points. It's very similar to finding absolute min and max, but guess what? We're not just over a certain little part of the domain. We want them everywhere. So what we can do, find the derivative and see where we have critical points, either where the derivative equals 0 or where it will be undefined. So we have to find the derivative. We're going to just, not -1, f prime of x. So first bring the 3 in front, subtract 1 from 3, so I have 3x squared. Bring the 2 down, 2 times 3 over 2 is 3x, and then -6. So I'm going to pause here to understand how we got this derivative, because it's going to be a little difficult. Definitely recommend knocking out the review assignments. Remember those ones that are the quick review ones that are not part of chapter 4, but they are part of your homework that's due. Recommend knocking them out sooner than later, because it's going to help you, because you have to be up to date and know what you're doing in order to be successful in chapter 4. Cool. So we found the derivative. Now we have to set it equal to 0 and see and solve for our x values. That would be our critical points. Quick question. So is it possible for our derivative to be undefined at any point? Maya, what do you think, ladies? Yeah, it can be undefined. Where would my...
Oh, not for this one.
Oh, no, correct. No. Sorry, I was not being specific. No, right, so this one, it can't be undefined because it's polynomial. It's defined for all real numbers. That's just the domain of a polynomial. But our derivative can equal 0, and all we have to do is solve for where it would be. So factor out of 3. And then this is the first thing you ever factor in algebra 1 is probably x squared plus x minus 2. Maybe the second thing, so as a negative. But you're looking for what adds to 1, multiplies -2, so you just have to factor it out. So I have x plus 2, x minus 1, and then I see my x values where this is true is going to be at -2 and +1. These are my critical points.
What happened to the 3? Oh, you divided.
Well, it doesn't give me a solution, right? My solutions only come from the factors.
Okay.
I could divide it out, but it doesn't affect anything.
And is it always going to have to be a polynomial, so you have to factor it and then you get 2?
It's not always a polynomial. So if you look at the next page, I think I have, B is not a polynomial.
So you could get 1 point?
You can get more than 1 point. You can get 1 point, you can get many.
Okay.
Yesterday, example 3, part C, we didn't find any critical points. We found 1 for B, and then we found only 1 for A.
Okay.
Sometimes we can find 2 critical points. You could have 50. It just depends on your degree of the polynomial. Because if you think about it, x squared only has 1 critical point because it goes down to a minimum and back up. X cubed depends on the polynomial. It could have 2. So the maximum number of critical points you could have is like 1 less than your degree. Yeah. Okay, so we found our critical points. Step 2, done. Almost. Are our critical points in our domain?
Yes.
Yeah, because our domain's all real numbers. It's just negative infinity to infinity, right? That's inside our domain, so we're good. Step 3, I'm just going through the steps that are above. So far, it's been very similar to what we've done before. This is the new part. Create a number line for our derivative. So I'm going to create a number line. Over here is going to be negative infinity. Infinity is over here. Of 1. Because we had our endpoints. Because before we didn't need a number line because we only wanted our absolute min and absolute max. But here we want all of our relative min and max. We want everything. I mean, technically, B is not all real numbers either. Our next example. When we're trying to find the absolute min and max for the whole domain, more or less, like that's when you do it. Okay. Okay. So we have a number line. This is going to be the number line for my derivative, f prime. So we label the points and any endpoints. Technically, we don't have any endpoints because we're going to infinity and negative infinity. I'm also going to use a number line in next lesson when I have 2 actual endpoints. So it's helpful to put any open circles. Any points are excluded in the domain. Do you guys have questions? Okay. Super rude. Step 4, use a number line, test values within each interval, and plug into our derivative. So I know that -2 and 1 are where our derivatives are equal to 0. I would like to know what's happening between. So these places where our derivative 0 means my graph is flat. If I have a positive derivative, that means a positive slope. If I have a negative derivative, that means a negative slope. So we literally can visualize the graph without actually putting it on graph paper. So if I have a number less than -2, maybe like -3, right? So if I plug in -3 in for here, I have 3 times -3 plus 2 times -3 minus 1. So this is going to be a negative number. This is going to be a negative number. What happens when you take a negative times a negative? Positive. Perfect. And then due to multiplicity, do you remember what that is? No, that's fine. There's a pattern. If I plug in 0, what happens when I plug in 0 into for here? Guess what? A positive times a negative is negative, and guess what the other side's going to be? Positive. Positive. Aha. Okay. So we can kind of imagine from negative infinity to -2,
It's going up.
our graph is going up. It says positive slope. And then at -2, it rounds out, has a 0 slope. And then between -2 and 1, we have a negative slope, so it goes down. And then at 1, we have a 0 slope, and then we have a positive slope going back up. So we roughly know what this is going to look like just by looking at the slopes, yes?
Could you just assume it was positive again? You didn't have to plug it in because you know it's going to go
Yep.
the opposite way.
That's what I mean by multiplicity.
Oh, that's
Flips.
multiplicity. Can it ever be 0? Like, can it like flatten, or is that normal?
Well, I mean, the flatten out. I mean, but then that won't be a critical point.
Okay.
So we labeled our critical points because that's where we turn from increasing to decreasing. What's wrong? Man, see,
I'm sorry, it's so funny.
there's only one, I know. I saw it.
Why is that fun? I don't know. Is it yours? Yes.
There's our phone, but no backpack. Okay.
Is
So
it yours?
as I was talking about, it's going. So it comes up. This is the part where it goes down, and then it goes up again. So you can see this is where a max occurs. This is where a min occurs. Yeah. So step 4 is like using the number line, test values. That's exactly what we did. We plugged in 3, right? -3, we knew it would be a negative number, right? Label the number line with a negative, where you get a negative number, a plus, where you get a positive. Where the number changes from a positive to a minus sign, that means it's going from a positive slope to a negative slope, that's where it has a max. And where it changes from a negative slope to a positive slope, that's where it has a min, because you're scooping down the bottom, yeah?
Okay, so let's say you did have a negative 2, and you have like negative infinity to 4 and infinity. Like anything between 2 and 4 would be a positive number, and 4 in.
So you mean if I had something like this, like here's a point, here's a point, here's a point. If this is positive, then it just alternates.
You can never have 2.
Right. Because all your critical points have a slope of 0.
So you can just find the first one, and then do that.
Yep.
But just check, like.
You can if you want, but it's pattern. As long as you found the correct critical points, you'll be fine. Okay, step 5. We talked about where it changes from a positive slope to a negative slope. It's a max, right? Because you see what I'm doing? Like, does that make sense?
No,
like,
yeah.
positive slope
and then
to a negative slope, that's where it's a max. Okay, and then negative slope to positive, it's where it's a min. It's scooping down from going down to up. Look, there it is visually. Okay, step 6. Define the min and max. Plug in the values from step 2 back into the original equation. So, I know I have a max at f of 2. F of negative 2, and if you plug it in, you're going to get a value of 11. Just plug it into this equation up here. And we have a min at 1. So at x equals 1, that's the location of my minimum. What's the actual minimum value? What's the y value there? Negative 2.5. Like, I trust that you guys can, like, plug in 1 into this equation and, like, do the math. You can do it. Okay. Yes?
Isn't technically 2 also a max?
No. No, it's not.
I have a question.
Because it's negative 2 and 1. Did I write 2 somewhere?
No. But,
No.
like, you see how it's a min at 1?
Yeah.
And then it goes back up?
And then it keeps going forever.
So then how...
So roughly this graph looks like this. That's what the graph looks like.
It doesn't just keep...
Nope, because it's x to the third power. X to the third power looks like this.
And we know that the max is at negative 2 because then it goes back.
Relative max at negative 2. These are the only 2 places where our slope is 0.
Okay.
Those are our 2 critical points, our 2 turning points. Yes.
So, if there's more than 2 turning points or more than 2 critical points, that would mean that you don't know which max. There's many maxes and mins, and they're all local. So you don't know which one's the absolute maximum. You don't know which one's the absolute minimum.
We
So
do.
we just have to plug them all in and figure it out from there.
So imagine instead of looking like this, imagine my graph looked like this.
Yeah.
Yeah, then we know that this would be an absolute max because it's the very, very highest value over the whole domain.
But the other one's a turning point too. So when
This
you're
one
doing
would be
it
a relative max right here.
Yeah, but when you're doing it on the table, on the graph, the number line, it would just appear as positive, negative, positive, negative, positive. Or, you know what I mean?
Yeah, that's why we plugged in the values to find what these would be.
Okay.
And then at the end, if I knew the end behavior, they're both going down, then I'd pick whichever one was the highest would be absolute max.
Okay.
Yeah. Cool. Keep on rolling. Okay. So B, we're gonna do the whole process again. First step, find our domain. This domain is not all real numbers. What values are cut out?
You gotta factor negative one and positive one.
Negative 1, negative and positive 1, so we have to factor it out. So we know that the bottom, x squared minus 1 cannot equal 0. So that means x minus 1 and x plus 1 both cannot equal 0. The 2 things that would make my bottom 0 are x equals 1 and negative 1. That's what I can't equal. So to write it in interval notation, I go from negative infinity all the way to negative 1, union negative 1 to 1, union 1 to infinity. So really, there's only 2 x values, and I just cut them out and I paste everything back together. Okay, domain, check. Next step, find our critical points. So we have to find the derivative. So I'm going to rewrite my f of x as x squared minus 1 to the negative 1 power. Just kind of helps us see a little bit. And this will be a great review on chain rule, which we need. Yeah, cool. So chain rule starting at very outside, and you have a negative 1 power, so you bring it in front. So you have negative 1 times x squared minus 1 to the negative 2. What? So this was my original function. I just rewrote it, and now I'm starting to do my derivative. Times, okay, so I took care of the negative 1 exponent. Now I got to go inside. Derivative of x squared is 2x. Yeah. That's it, times 2x. Because I'm done. Right. This is what you do on your final, I think, right? Yeah. You just like kept going. That's like the second derivative. We only want the first. Because the first thing we did was take care of the fact that we have this exponent on the outside. Okay. Then we took into account the function inside, the x squared minus 1. If this was 2x squared minus 1 to the negative 1, then you could like take the derivative of what's very, very inside. Yeah. Okay. Okay, let's rewrite this. So my derivative is going to be negative 2x over x squared minus 1 squared. Okay. We're cool so far? We're good so far? And if you're like, man, chainy chain, gotta like go back and review it. Maybe come to bonus. Maybe be like, hey, math center boy. Or be like...
It's not very helpful. Math center boy is not nice. Sorry.
You're not nice. Okay. You can come to bonus. You can email me. There's a thing. It's absolutely brand new and it's groundbreaking called Google. You can search like chain rule.
Yeah, there's videos before the final. Or you guys can hang out. It's okay.
Yeah. Or ask a comrade. Ask a comrade here. Chain rule.
I appreciated it. And it just came off as weird. Like I wanted to lunch with all you guys.
That was not nice.
I had lunch with you today, so.
Wow. Okay.
You said it equals 0.
So, exactly. So, I want to find my critical points. Now that I found my derivative, I want to find my critical points. So, I'd like to know where is my derivative equal to 0, and where is my derivative going to be undefined?
Negative 1 and...
So, where is my derivative equal to 0? At x equals 0.
Oh, it's undefined at
Because in order for this to equal 0, the top has to equal 0. Yeah, so where my numerator equals 0, that's where my function equals 0. So I was looking where, I'll show more work just for you. Negative 2x equals 0. What x makes it? An x value of 0 makes that true. Okay, that's one critical point. I want to find my critical points. You set your
entire thing.
You set your derivative equal to 0 or where it's undefined. Where is your derivative equal to 0 and where is your derivative undefined? So,
Why are you only saying the top?
Because if the top is equal to 0, your whole function's 0. If the bottom equals 0, that's where you're undefined. So now I look, where is the bottom equal to 0? So when x equals plus or minus 1. So I have 3 critical points, 0, negative 1, and 1. These are my critical points. Woo, 3 of them. But I have to look, right? So go back, blah, blah, blah. Step 1, find domain of function, check. Step 2, find critical points. Cool, we did that. Check that they're in the domain. One and negative 1 are not in my domain. Because what's happening at 1 and negative 1?
There's a hole.
There's a vertical asymptote.
Oh yeah, because it's the bottom.
Yeah, it's a vertical asymptote at negative 1 and 1. Because if you look up at the top original equation, it's cut out from my domain. When the bottom of my original function is undefined, that's where I have a vertical asymptote. So since 2 of the critical points I found were not in my domain, I have to draw circles for them. I promise you, we're almost done. This problem, we're almost done. So go from negative infinity, here's positive infinity, -1, 0, because I'm going to draw a circle. So I have a hole here, and I have a hole here. So if you look at your directions, step 3, create a number line for f prime of x, label any critical points and endpoints. It's also helpful to put open circles at any points that are excluded in the domain. That way we kind of know what's going on. Yeah. And you'll see why.
Are they asymptotes or are they holes?
They're vertical asymptotes. But that means at that point I won't have a derivative. So if I was drawing a graph of my derivative, there would be a hole there.
Okay. He's the one that's...
Wow. I think that was loud enough. I think we could like watch the screencast and listen to it. It's really loud. Okay. Guys, I just okay, definitely no. Seating chart. And you know who's sitting the furthest away from each other? You two. You two are sitting the furthest away from each other. As much as they talk, at least like, you know, they don't curse. Sure. What? I am. 100%.
I thought you said this semester we can say where we want.
Yeah, it's an experiment until people mess it up. No. It's going to be for everyone. It sucks to suck. Okay, so just going through the steps. Come on, if this is like easy.
Can I explain this?
Step 4, use a number line, test values. So if I'm less than 0, guess what's happening? Am I positive or negative?
Negative.
What?
I just guessed.
The derivative. We're looking at the derivative. Look at the derivative. When we're less than 0, am I positive or negative? Less than 0. So let me pick a number. How about like -2? Let's plug in -2. -2 times -2 over -2 minus 1. Let's see, squared minus 1 squared. The bottom turns positive. The top turns positive. This is positive. What happens? Do I switch now between -1 and 0? No.
And you did. Wait.
So I can.
Because there's a vertical asymptote, so they both go up.
Yeah. Which means this means your original graph look like this.
So the other side.
Something like that. So it means the other side's coming up as well.
So here's where I have to
No, the other sides are negatives, yeah.
come in.
So look something like that. Is roughly what your graph's gonna look like.
So 0 to infinity is negative.
Hold on. Positive. Something like this. So this is negative and this is negative. Let's plug in and see. What if I plug in like -1/2?
Wait, before you go there.
So a negative times a negative over, well, let's see. This is squared. The bottom's squared, so it doesn't matter what you plug in, it's always going to be positive. Does it make sense? I'm not actually doing the math. Like, I'm just plugging in positive negatives to see if it's going up or down.
Yeah.
Okay, so I'm expecting you to pay attention. I'm not going to answer your question until you stop laughing and pay attention. Like, I'm done. I'm over it. So, plug in -1/2. And negative times negative is positive. Doesn't matter what you plug in the bottom, it's squared, it always turns positive. So anytime you plug in a negative number, everything less than 0 is going to be positive. Guess what happens when I plug in a positive number? A positive times a negative is negative. Oh, positive down here doesn't matter, it's squared, it turns positive anyway. So everything greater than 0, that's x, that I plug in is positive. Everything less than x, that I plug in is negative, will be positive. Did I say that backwards? No. Hopefully that makes some sense. Okay, so then we look I'm just going through the steps, blah, blah, blah. Where it's positive, get a positive value. Where it's negative, get a negative. Step 5. Where it changes from positive to negative, you have a max. So I'm going up. What?
How do we know where the max is?
So it's going up, going down, going down. Where you switch from going up to down is a max. Right here is 0. So at x equals 0, you have a max. So your maximum is going to be at f of 0. If you plug into your original equation, you have 1 over -1, so it's just -1 is your maximum value. Okay. Question, Tal. Yep.
So one, I understand for this problem specifically, it doesn't matter what number specifically you plug in. So like, let's say I have a polynomial or like whatever it is bigger than that. So you get polynomial because like a -4 could be positive and like a -3 could be negative.
So if it's a polynomial, it always switches plus minus. But since it's a rational function, you don't know if the graph is going to look like, you don't know, okay, so it's going up. You don't know if it's going to come back down this way or if it was coming up this way.
Well, like, what if you have...
That's why we had to check between those two. Does that make sense?
Yeah. I just, like, I'm trying to think of an example when you have, like, like 6x cubed minus like 2 squared, 2x squared minus 6. Like, you plug in like one positive. I don't know if that's ever in the
So, talking about polynomial here, we plugged in a number that was between -infinity and -2.
Can it ever happen where like two negative numbers, one could be positive and one could be
Not if you have a polynomial. Polynomials always switch. But if you have a rational function, like what I was talking about, you don't know if it was like coming back up or if it was going down. In a rational are a ratio of 2 polynomials. That's literally the definition of it. Yep, 100%. That's what we're doing.
Sorry.
You think I made this up? No, I wish I made this up.
Who did make this? I don't know why.
Newton, Leibniz.
Newton stole.
You know a lot this time.
Yeah.
Yeah.
You're just jealous of his brain. All
Newton got it on
No, he did
right. No,
not.
he didn't.
He did not.
He published all his major works by 23.
Why is
I retired by 23.
Yeah. All right. Let's keep going. Let's keep going. Let's keep going. I would like to start 4.2 today. I'd like to keep going. Okay. Patience.
Okay, so the first step is to find the domain.
It's fine. I'm just going to mark people off. So at the end of the semester, when you come crying to me about your grade being 0.2% from the next one, I look through and I see how many times did you have your phone? How many times were you talking? How many times were you late? And that helps me justify. How many times did you come to bonus? How many times did I have to stop because I got frustrated at you because you're talking to your neighbor? So, there's actually at least like half the class, if it comes to like a 89.49, I love you, but sorry, that was the grade you get. No, it doesn't. That's not the way it rounds. 89.49 is a B+. Because it's fair. If I have to stop class and wait for you to stop talking because you're on your phone because you're talking to your neighbor, no. Goodbye. No, goodbye. That's a B+. I will not round for that. If you're constantly in class, paying attention, not being a jerk to me by talking when I'm trying to teach you a lesson, so that way I can have more class time to go over worksheets and just more problems so you understand it, so you don't have to spend so much time at home Googling things. That would be great. So that's what I look at. There's a couple times where I'd like round where it's like, okay, 89.4, but they're always in bonus. They're like on it in class. Of course, you can have that 105% participation. But like, this is what I judge it on if you're questioning. Because I try not to go off my feelings. I try to go off hard facts. So I literally write down and see how often were you not in school? How often were you talking? How often did you go to the bathroom? Yeah. Cool. And I don't like being petty and like marking this down and blah, blah, blah. Because I'd hate for someone to do that with me, but I also would never be disrespectful like that. So, cool. Example 5. Identify the critical points and determine the local extreme values. First thing we have to do, identify the domain. What's the domain? Do we know? Is it defined for all real numbers? Yeah. It is. Because look, everywhere less than 1 is defined by the first function. Everywhere greater than 1 is defined by the second. And at x equals 1, it's the top. So any x value will always have a y value. Cool. Okay. So we need to find the derivative. No surprise, the derivative of a piecewise function is also going to be a piecewise. The derivative of the top is going to be a negative 4x. Derivative of the bottom is just 1. And you have the same constraints. Because derivative of negative 2x squared is just negative 4. That's it. So let's look for our critical points. Are there any points where it would be undefined? No, because 1, 4x, they're both lines. Okay, then I look for where my derivative would equal 0. So when negative 4x equals 0, let's see, my critical point is at x equals 0, which makes sense because that is where an x value of 0 would find its derivative. So that's fine. But we also need to be careful. Because it's a piecewise function, what can happen that can affect the differentiability, right? So remember, if it's discontinuous, like a hole or a jump or an infinite vertical asymptote, or the birds I used to draw, right, cusps, or corner. Ooh, so we got to check for a corner. Since this is a piecewise function, we got to check for a corner. Where should I write this? Maybe over here.
But does that matter? Because it is, we're just looking for.
Because that's something special happening. So piecewise functions, you need to check for corners.
But isn't a corner the same thing as like a rounded thing when it comes to a strict value? Not necessarily. Not.
Because the thing with a corner, you could have a function like this, where technically there's no critical points, right? Because there's not a place where a slope is equal to 0, right? There's no place, but technically right here, it's not differentiable, but that is a max for my value. Okay, so hopefully that illustrates why. I should probably just draw this somewhere. Let me draw that over here. So if I would draw my function, it would look something like this. Let's see. When x equals 1, I have a value of 3. And it goes up like this. That's the first part of my function. And then it's x plus 2. So that's what my function looks like. This is f of x. So I do have a critical point right there. So I'm justifying why we have to include x equals 1 as a critical point, because that's the place where we have a corner, so it's not differentiable there. I can't take a derivative at x equals 1, so I have 2 different slopes as I approach it from both sides.
But the only way to check that
is to realize that you have a piecewise function. Repeat it. It may have the same slope at the place where you're switching, though. I know I've done that to you before. So, for instance, I could have a piecewise where it's like x squared and 2x, and let's have it be at x equals 1. Like at that point where I'm switching, it would have the same slope, so it would be a seamless transition. Versus like 2 different hard slopes coming at each other. Yes?
So
I'm going to come back to you on that.
Because the slope on the first one is 2, and the slope on the second one is 1.
The slope on the first one is negative 4x.
Oh.
And the slope on the second one is 1. So if I was going to draw the derivative, it would look like that. This is the graph of the derivative in blue.
Okay.
The one in...
So it's a corner. Okay.
Yeah, it's a corner.
And how do you know? You just have to check if it's okay.
You check for a corner because you say, are these the exact same number at x equals 1?
No.
No. So that's how we check for a corner. I say, okay, at x equals 1, from the left, my slope is 4. From my right, my slope is 1. Okay, so now that we have our critical points, we're going to label them on a number line. Let's see, we're going from negative infinity to infinity, and there's 2 points I have to include, 0 and 1. Oh yeah, I totally did not draw my left side correctly. Should be something like that. Because we have 2 critical points. We have the place at the top of the parabola for the piecewise part, then we have the conjoining portion, because that's a local min. Okay, so if I plug in a number less than 0, what do I get? So we're plugging into our function value. So if our number is less than 0, we're going to plug into this top one. So we're plugging into our derivative. It makes it positive. And if I plug in a number between 0 and 1, negative. And if I plug in a number greater than 1, positive. Okay. So that means it's going up here, going down, going up. Which means that I have a maximum right here, a minimum right there. Wait, okay, tallest question and then Spencer. Where? No, well, between 0 and 1 is negative, because between 0 and 1 is a positive number. Negative times positive is negative. But then once I hit 1, I plug into the bottom one and it's positive. Okay, let's plug in 1/2. 1/2 is less than 1. Half of negative 4 is negative 2, which is negative. So it's negative. Okay, we're almost there. We're getting close. So I have a local max, I have a local min. I just have to plug in 0 into my function to see what the value is. I plug in 1 into my function to see what the value is. Yes? Wait, did I get your question, Spencer?
You answered it.
Okay.
That's not the max, though. That's a local max. It goes towards infinity
Correct.
because the domain is
Yes,
towards
this is how
infinity.
you find the local maximum.
But that's not. Is that the extreme values we're trying to find? Local.
This is the local, the relative min and max.
Don't you want us to find the absolute or
No, so this section right here is for the relative, right? Local. Nope, it's fine. It's been 2 days. Okay, so let's find the actual value. So my max is going to occur at 0. So if I plug in 0 into my original function, plug it in this top one, 5 minus 0 is 5. And then my local min is at 1. And if I plug this in, I get 3. So to find the actual y values of my max and min, I plug into the original function. But to find these positives and negatives, we plug into the derivative function. Perfect. So I think we can get through at least one page of the next notes. I think we could do that. That would be pretty helpful. That'd be great. Yeah. Do we have questions over this so far? Okay, I'm glad I put this as 2 days. Originally planned it as 1. It is what it is. It's all good.
good intuition?
Yeah, I tried spreading chapter 4 out for you guys. Okay, so we talked about the extreme value theorem. Now we're going to talk about the mean value theorem. Oh my gosh. What does it mean to have a mean? Average. Literally, that is what the mean value theorem is. Okay, you have two endpoints, and if you take the slope between them, right, the secant line, the average slope between them, the mean value theorem says there has to be at least one place where that average slope is the same as the tangent slope, right? That's what this is showing right here. So, in other words, if you have a function that's, oh my gosh, why did this happen? No. So some of these other teachers use this highlighter button, and so I'm trying it, but it's not working out for me. Nope. You know what? It's fine. It's fine. Whatever. I'm done with this. Yes, I do, but I deleted them, so I'm trying to be more organized. Do you see the right side? It's more organized now. I'm really taking this thing too far. Okay. There you go. If f of x is continuous at every point of the closed interval, I'm going to delete that one. That's dumb. Okay. Continuous at every point of the closed interval. Okay. Ready for this? I have two endpoints. It's continuous between. Literally, you start at your endpoint, you can draw the line between it. That's all it means, continuous. Continuous between them, you include the endpoints, and if it's differentiable every point, aka no cusps, no corners, no vertical tangents, no discontinuities of jumps, right? It's continuous and differentiable. That means if you take the average slope between those 2 points, there has to be at least one place where that actually is the slope of the tangent. That's what this is showing right here. If I take the secant, aka the average, this is the normal slope you find. It's the slope equation, y2 minus y1 over x2 minus y1 over x1. So whatever, you know it. There has to be at least one place where it matches. Kind of cool. That's all it means. Yeah, it's the, let me be specific. The one in green right here, this is the average slope of the secant. Okay, so state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval, aka, does the secant slope match at least 1 point's tangent slope? That's all we're proving. If it does, find each value of c in the interval a to b that satisfies the equation. Okay, so so what we're trying to do, I'm just going to rewrite this as f of b minus f of a over b minus a. So here my a is 0, my b is 2. So I want to do f of 2 minus f of 0 over 2 minus 0. So notice everything associated with 2 is on the left, zeros are on the right. Now you could flip them. You could say f of 0 minus f of 2, but then on the bottom you have to do 0 minus 2, right? So that makes, I don't know if that makes sense what I'm trying to tell you, because this is what people get wrong. There's been a couple times where people switch the bottom, even though they put f of 2 first, f of 2 here, the 2 first here, they put the 2 on the right side. Okay. Figure if I make you aware of common mistakes, you can double check yourself. Okay, so I have this. Let's see. So f of 2, so if I plug 2 into my function x squared, 2 squared is 4, 0 squared, 0, over 2 minus 0, which is, 2 minus 0 is 2. So I'm looking for where the slope is 2. This is the average slope of the secant, which is this line right here. The one in green that I horribly wrote. It has a slope of 2. Well, I would like to know where on my line x squared is the slope exactly going to be 2. So we have to find the derivative. And then we set it equal to 2. How do I find the derivative? Yeah, bring the 2 down. So 2x. So if I want to know where is my derivative equal to 2, well, okay. So it's saying f of c, right? F of c
isn't that
is your
2x
derivative
minus
that we're looking for. So f of c is literally going to be 2x. Where is it equal to 2? Oh, when c equals 1. Okay. I should stick with the notation your book is saying. All the c is the magic number we're looking for. It's the x value where its tangent slope, the slope of the tangent is equal to the secant slope. That's all the c means. That's how your book uses it. Because the equation's right here, f of c, so at some point, the derivative at some point is equal to the average slope of the secant. So I found the average slope of the secant is 2. So I'm looking for what value of x satisfies. So 2x is equal to a value of 1. Okay. Sorry. Up or down? Is that better?
Yeah.
I did let you sit anywhere you wanted, so. I did not make you sit there, so.
I'm confused by
Look at this happy row in the front.
Look at all of them.
Yes?
The last part, so I understand that 2 is the average slope of the secant, and we're trying to find where x is to satisfy that the slope is 2. So I don't understand the part. I don't understand the part blue.
Okay.
Yeah, we'll go light up with
Okay. So this part blue, I was trying to show you what your book says. This was finding the derivative of our function. Then I know that at a point, which they call C, because it's some point between my two bounds, at one of those points, the slope of the tangent has to be the same as the slope of the tangent at that point has to be the same as the slope of the secant. Yeah.
Okay.
C is just the point in your interval. It's our magic number where its tangent slope is the same as the secant.
But why is 2c equal to?
Because this is the secant. So I'm setting setting it as the secant. Okay. Should we try one more? Yeah, let's try one more. Okay, so let's go ahead and let's graph this. Right, what does absolute value of x plus 1 look like? It's a v. What up 1? Okay. So it is a corner. So if I was looking at this, the derivative of x equals 0, it's non-differentiable. But between -1 and 1, okay. So I need to find, let's see, f of b minus f of a. Let me actually write out the whole thing over b minus a. So f of b, so 1 minus 1 over 1 minus 1. Oh my gosh, something crazy is going on here. So if I was going to connect -1 and 1 with a line, what's the slope? Where is 0? Where is my slope going to be 0?
1 and -1.
No, never. So it doesn't actually apply. The mean value theorem does not apply.
Wouldn't it be undefined? Which would be the slope.
You know, I shouldn't even wrote the things in blue because it's not differentiable. To even apply the mean value theorem between your two bounds, it has to be differentiable, and we have a corner at x equals 0. So
wait, it's corner cost, and then what's the other one?
vertical tangent and discontinuities.
Okay.
Does not apply. It's not differentiable at x equals 0. So I should not even wrote this because it doesn't even apply. Let's erase it. It's a good place to stop because the next one will take longer. So next class, we're going to finish the second lesson. So that's not too much more, like 2.5 pages. Cool. All right, so I'll see you guys Thursday.